This is AP Podcast 9.3, and we're going to talk about cell potential, equilibrium, and then the Nernst equation. So, cell potential can be used to calculate Gibbs free energy, which we talked about in the last chapter. So, Gibbs free energy is equal to negative n, and n is the number of moles of electrons. What you're going to do is you're going to look at the different balanced half reactions, and say there were 2 electrons in those half reactions. That's what will go here is the number 2. Or say there was only 1 electron when you were balancing out those half reactions, then a number 1 would go there. That's how you determine what n is. F is Faraday's constant, and sometimes you'll see this rounded to 96,500. So either of those values is acceptable. And then E is the cell potential at standard conditions. And remember, that's measured in volts, and volts are also joules per coulomb. And you're going to remember that because I'm going to show you how all the units will cancel out here. Things you need to know then in relationship to whether something is spontaneous or not. If the cell potential is greater than 0, so if we get a positive voltage, and the Gibbs free energy is greater than 0, then this is going to be a non-spontaneous reaction because the Gibbs free energy has to be a negative number. It has to be less than 0 in order for it to be spontaneous. So that's what we see right here, is that if the voltage of the cell is greater than 0, so it's positive, and the Gibbs free energy is less than 0, so it's a negative, that's how we're going to get these spontaneous reactions to occur. Okay, practice problem number 1 says using a table of standard reduction potentials, calculate delta G for the following reaction. And here's what we have. It says, is this reaction spontaneous? So the first thing I'm going to do is calculate delta G, and then I'll answer the spontaneous question or not. But what I want to do is make sure this is balanced, and I'm going to do that by writing half reactions and checking charges and checking numbers and all of that stuff. So I have aqueous copper ions, and they're going to form solid copper. And then I have solid iron, and it's forming the iron 2 ions. So with this, I have to add 2 electrons to balance out the charges here. And on this one, I'm going to have to add the 2 electrons down here. So since I have 2 electrons on both sides, those are going to cancel each other out. And it turns out that this was the balanced reaction. So we take our copper, and then the iron giving us the solid copper, and the iron ions. Okay, the next thing we want to do is I want to calculate the cell potential of this thing. So I'm going to look up the half reactions on my table, and for the copper one, it is 0.34 volts when you find it. And it's written, this is a reduction reaction, so we're going to keep the voltage the same. We're not going to do anything to that. For the iron though, the iron's being oxidized, so we want to flip the sign of the voltage that we find. And on the table, it's a negative 0.44 volts. So we're going to use a positive 0.44 volts. Since it's doing the opposite, it's being oxidized. That means the cell potential is those two added up, which, we'll put a little plus sign there so we remember, is going to be 0.78 volts. I am going to use that in that equation that we just talked about, the negative NF E. So negative n, and remember we said was the number of moles, and in this case it's 2. So 2, and then we have, and we want to put the units because I want to show you how those cancel. So we have 2 moles of electrons, and then we have the Faraday's constant. I'm going to use the 96,485, and that is coulombs per mole of electron. Do it that way. That's kind of confusing since it's MOLEE. And then we have the cell potential, which we just calculated. And instead of using it in volts, I'm going to use it in the joules per coulomb. So there I plugged everything in. My moles of electrons are going to cancel, and the coulombs are going to cancel. What I'm left with is joules for my Gibbs free energy. So delta G, if I do the math there, is going to be negative 15051, and we'll round that up to 7, and that would be joules. Because that's such a big number, I'm going to go ahead and put that in kilojoules. So that's going to be we'll say negative 100 or 151 kilojoules. So answering the part that says, is this reaction spontaneous? Because the cell voltage was positive and delta G is negative, yes, the reaction is spontaneous. So that's how you do those. You just take the cell potential and you plug it in to this new equation that we're using that involves Gibbs free energy. All right, galvanic cells. Up to this point, we've been using the same molarity, the same concentration on each side of the galvanic cell. So galvanic cells are made of substances with the same molarities, and it's 1 molar because that is a standard state. We said that standard states for galvanic cells is 25 degrees Celsius and 1 molarity for their concentration. Concentration cells are made of substances with different concentrations that are not at standard states. And because they're not at standard states, you can see here they're missing that little 0 sign that I guess I would call it E0 of the cell, and that stands for standard states. But because we're using concentrations that are not 1 molar, we can't add that little 0 sign up there. So qualitatively, we can predict the direction of the change in E. So we can predict, is the cell potential going to go up or down? And that's using Le Chatelier's principle. The electrons are transferred in the direction that will make the concentrations of the ions the same. So they're looking to equalize the concentrations. One needs to go up and one needs to go down. And the example that I have here involves silver nitrate. And you can see that this is unusual, but because this is a concentration cell, I can use the same substance in both cells. I have silver nitrate here and silver nitrate here, but because I'm using varying concentrations of them, they're different, I will actually get a voltage produced, and I'll be able to tell what I get. And because we are going to get the electrons to flow in order to equalize these concentrations. So what we're going to see though in this one, because this is 0.1 molar silver ions and this is 1 molar silver ions, this cell is going to flow in a way in order to equalize this concentration of the silver ions. So they want to flow in a way that this number will go down and this one will go up. So what we're going to see is, in order to make this 1 molar go down, I need to get rid of silver ions. So the electron needs to come this direction, form with the silver ion, and be plated onto the silver electrode. That will drop this concentration. So the electrons are going to flow this way. They're going to flow to the 1 molar solution because as they come in, each electron is going to join with an ion and it's going to pull it out a solution. It's going to become solid silver. It's going to form on this electrode. So this number is going to go down. And then over here where we're removing an electron, we're oxidizing the silver from the electrode, loses its electron and becomes the silver ion in solution. So this number is going to go up. What that means then is this is acting as the anode and this is acting as the cathode. The anode is where the oxidation is happening, so we're losing electrons. The cathode is where the reduction is happening and we're gaining electrons. And as this flows, eventually it will stop once the concentrations equalize each other. All right, our question that we're dealing with though, practice problem number 2, gives us this reaction between solid aluminum and the manganese ions. So we have our half reaction, our half reactions have been balanced to give us our overall balanced reaction. And it says predict if the concentration or if the cell potential that's not at the standard states will be greater or less than if this were at standard states. So the standard cell potential. If we change concentrations of the aluminum ions to 1.5 and the manganese ions stay at 1. So if I wanted to draw this in here so we could see what's happening, I'm going to have manganese and I'm going to have 1 molar manganese ions down here. And then on the other side, I'm going to have aluminum as the electrode. And I'm going to have 1.5 molar aluminum ions in solution. So if we want to think about this, I want to lose the aluminum ions and gain the manganese ions. And if I look up here, what that tells me is it's going to want to shift backwards. It's going to want to go in reverse because I have more of this, and in order to establish a new equilibrium, it's going to want to shift back to the left. So because there's going to be a favored reverse reaction, we should see that the cell potential that's at these conditions, it should be less than what we would have expected to see had these both been 1 molar. So because this is going to actually shift in the opposite direction, what it normally wouldn't do in order to compensate for this uneven concentration that's going on here, we're going to see the cell voltage appear lower than what we would expect, and that's because of that reverse reaction. So the electrons are going to want to flow this way in order to neutralize what's going on here. Then the next question says, if we change the aluminum to 1 molar, and this is still aluminum, and the manganese becomes 1.5, and this is manganese, we can see that we now actually have more reactant than we should. So more reactant means we're going to shift to the right, which means our forward reaction is going to be favored the way that it's going to run anyway. And if it's going to run this way, forward, manganese to aluminum, which means the electrons are going to go this way like they should in order to equalize the concentrations, because we're getting more of a forward reaction than normal, we would expect to see the cell potential of this concentration cell to be greater than what we would predict using the table of standard reduction potentials. So in this case, it's going to be higher because the forward reaction is favored. So you just need to be able to look at these and kind of use Le Chatelier's principle to predict, are we going to see more of a forward reaction, or are we going to see a reverse reaction? If it's a forward reaction, it's going to make the cell potential go up. If it's the reverse reaction that we're going to see, we're going to watch the cell potential go down. So that's what we do with concentration cells. The Nernst equation is the last thing we're going to talk about here. And what we have is, this is Gibbs free energy, but not at standard states. That's equal to Gibbs free energy at the standard states plus RT natural log of Q. And remember, we're using Q because we're talking about Gibbs free energy, not at equilibrium, not at standard states. So that's why that's Q and not K. They just plugged in that first equation for the G's here. That's all they did. And then what you end up with is this reaction once we do a bunch of rearranging, which is the Nernst equation, minus RT over NF natural log of Q. So once they rearrange this, you end up with this equation, which a lot of the times when we use it, they've actually solved for some of this, like the RT and F, assuming 25, this is assuming 25 degrees Celsius, they can plug in some of those numbers, and then it's even rewritten as this. So the cell potential at standard states minus 0.0592 over N, N being the number of moles from the balanced reaction, log of Q. And yes, this is log, not natural log. So these are the Nernst equations written 2 different ways, one this way, one that way. This is probably more common in what we use because it's usually at 25 degrees Celsius, so it's just faster. It's less you have to plug in if you use that guy. Okay, as reactions proceed, concentrations of products increase and reactants decrease. And when we reach an equilibrium, we know that's where Q equals K for the equilibrium constants in the quotient product. And then we have the cell potential is also equal to 0. So if the cell potential is 0, remember this was just a normal E right here, we set that equal to 0, we do rearranging, and then we end up with this reaction, or this formula down here, which lets us solve for the K, the equilibrium constant. So there's another way that we can use the Nernst equation to find the equilibrium constant if we're looking for it. All right, this is the last practice problem we're going to do together. It says, what is the electrical potential for the following cell with the following concentrations? So I have my reaction here. It's not balanced, and they've given me concentrations that are not all one, so I'm going to have to pay attention to those. The first thing it wants me to do, because I'm looking for the electrical potential, I'm looking for normal E, not E naught. I want to write a balanced equation. So I want to take this thing and balance it. I'm going to do that through half reactions. So I have this VO2 with a positive charge, and that's going to form VO2 plus. And then my other one is zinc going to zinc plus 2. And I'm going to do this guy first because it's much simpler than the top one. So that one's done. Up here, though, I have 2 oxygens on this side and 1 oxygen here, so I'm going to add a water. And then I have 2 hydrogens, so I'm going to add 2 H pluses to this side. And then I have a charge, overall charge of 2 plus and an overall charge of 3 plus. So I have to add an electron over here in order to get the charges on both sides to balance. And then I'm going to have to multiply this thing by 2 because I need the number of electrons to be equal. So after I do all of that, I'm going to rewrite it down here. We're going to have 4 hydrogen ions plus 2 of the VO2s plus a zinc gives me zinc ions and VO, 2 of those, 2 plus, and 2 waters. So there's my overall balanced equation. The next thing it wants me to do is calculate the cell potential at standard states. So I'm ignoring the fact that these are different concentrations. We're just calculating what would this be if it were at standard conditions. So I look up each of these half reactions on the standard reduction table of the potentials, and what I find is this first one is 1.00 volts, and this guy right here is negative 0.76 volts, but this is the oxidation reaction, so we need to flip that sign. So it's going to be positive 0.76 volts. That means the cell potential at standard states is going to be 1.76 volts. And I'm going to remember that because I'm going to have to use it in the third step that says I need to use the Nernst equation and find the cell potential with these concentrations. So the cell potential is 1.76 volts. I'm going to rewrite that quickly so I don't remember, or I don't forget, is 1.76 volts. All right, now I'm going to use the Nernst equation. And we said the Nernst equation was this guy. And I'm assuming that this is at 25 degrees Celsius. They didn't tell me otherwise, and that's kind of the default temperature if they don't tell you. So I'm going to use the shorter one that has less things to plug in. So there's my equation right there. I am looking for the cell potential that's not at standard conditions. I just calculated that guy, so 1.76 volts minus 0.0591, and this N would be 2 electrons, because remember we had 2 electrons on either side of those half reactions. So that's going to be 2. And then we take the log of Q. And Q, what I'm going to do first is just write what you should have for the concentrations when we go to plug this in so you can see where everything went. Products over reactants, do not do liquids, and do not do solids. Remember, those things don't have concentrations. We don't do those in Q's and K's. So just the aqueous things, just the ions. So I have zinc ions, and I have the VO plus 2. And there was a 2 in front of that in that overall balanced reaction, so that's squared. On the bottom are your reactants, and there's also only 2 ions on the reactant side. There were hydrogen ions, and there were 4 of them, so I need to put to the 4th power. And then the other one is the VO2 with the plus charge, and there was a 2 in front of that one, so I need to put a 2 here. So what I'm going to do is just rewrite this, and I'm going to plug in then the concentrations that they gave us. And I can't see them, but you should be able to look up at the question and see where we're pulling these numbers from. Okay, so if I look up in the question that they gave us, I look up the concentration of the zinc ions, and it's 0.1. So this is going to be 0.10 molar, and I don't do anything to it. Then I look up the VO plus 2. Make sure you get that one, not the other one, because they look very similar. That one is 1.0 times 10 to the negative second, which would be 0.01 molar, and that needs to be squared, divided by the hydrogen ion concentration is 0.5, and that one needs to be to the fourth power. And then the VO2 with a plus charge is 2 molar, and that needs to be squared. So I just pulled those concentrations from the original question, and then we plug all this stuff in. We still have that, and then when I take this side and put it into the calculator, I end up with 0.13. So this guy has that final voltage with those concentrations. So the cell had, oops, that's not a minus, that's a plus, or else that wouldn't make any sense. So this is 1.76 plus 0.13, and we get 1.89 volts. And that is the voltage we would see with those concentrations if we did it in this cell. So there's the Nernst equation, how we can use it. That's it. Concentration cells and the Nernst equation, those are the two big ideas that you should be able to do. Both of those kind of have the formulas or Le Chatelier's principle that goes with it. Also the Gibbs free energy, being able to calculate that from the cell potential and the moles of electrons and Faraday's constant. So big three ideas that you need to pull out of this podcast, and we'll practice more in class.